Good day, everyone. Today we shall be considering complex number, and this is a part 3 of our complex number. By the way, this is Gifted Boy, aka Saizu, first in Africa, sixth in the world. Please do well to subscribe to our YouTube channel if you are enjoying our work, and on your notification button so you'll be notified when we drop other tutorial videos. Today we are looking at representation of Argand diagram. So representation of complex number using Argand diagram, and then the polar representation of a complex number. The Argand diagram is a graphical representation of complex number. When you represent complex number on your graph, you call it an Argand diagram. That's actually an Argand diagram. You see, a complex number actually is generally written as Z is equal to A plus B. And now you see this A. The A is known as the real part. The A is known as the real part. And then the B is known as the imaginary part. The B is the imaginary part of the complex number. Please, not BI. B. Imaginary part. Yes. Imaginary part. And now we can represent this complex number Z is equal to A plus BI on the graph. And it's all written like this. Let's say we have something that looks like this. This is our graph. You see, the real part is written on the x-axis, while the imaginary part is written on the y-axis, or you say y-coordinate. Now, the A, because A is the real part, I'll represent it somewhere on the x, and it's a positive A. And then the B, represented on the y-axis. And then we can write like this. This is our complex number, Z. So this is our Z. Z. Yes, which is actually equal to A plus BI. Yes, this is our complex number. And so, the real part, remember, on the X, while the imaginary part on the Y. Let's take an example under this. The question says, represent Z, which is equal to 4 plus 3i on the Argand diagram. Well, this is quite easy. All we just need is to draw our graph. Our X and Y. And then you can see, as you look at this question, 4 plus 3i. 4 on the horizontal. So I can just take my spacing as 2, an equal interval of spacing on your graph. You know, your graph has scales. So you have to scale your graph for it need to work. And then the imaginary is 3. The imaginary part on the Y is 3. So this can be my 1, my 2, and 3. And so I can draw my graph now. So connect the two important points. So we are good to go now. So this is my Z. So that's all. That's all. Let's take example 2 now. Example 2, represent the following on the Argand diagram. Then we can scale our graph. So 2, 4, and then 6 here. Here we could have 1, 1, 1. So that's it. 1, 2, 4 here, 3, 2, and 1. And this could be -1, -2, -3, and -4. So this will be again minus 2 minus 4 minus 6. Okay, and so we can now go ahead to represent. For the first one, z1 minus 2 plus 3i. So minus 2 on the x-axis, but this is minus 2, so it should fall on the negative x-axis since it's minus 2. So I'm talking about a point that exists here. And then we have 3. This is 3. So we can go ahead now to connect those 2 points. So this is what we have. So my z will look somewhat like this, my z1. So that's our z1. We also have a z2. The z2 is minus 1 minus I. Minus 1 minus I. Minus 1 on the negative x-axis. So it will be somewhat here. And then minus 1 on the negative somewhat here. So I join those 2 points now. So this will be my z2. This is my z2. Again, is my z3. Minus 5 plus 2i. Minus 5 on the x-axis. So my 5 on the x-axis will be like here. And then again plus 2i somewhat here. So I'll connect those 2 points. This is what we have. So we can go ahead to join to the origin. Sorry. So this is our z3. Z3. Again, our z4. The z4 is 3 plus 3i. 3 on the positive x-axis, so somewhat here, and 3 on negative positive y-axis, somewhat here. So I can join those 2 points together now. So this is just simply the Argand diagram. Very, very simple. Very, very simple. My students will always say everything is simple to me. Well, actually, nothing is difficult. Z4. And then finally, minus 2 minus 2i. Minus 2 minus 2i. Well, let me just change this z5. Let me say it is plus 2 minus 2i. Plus 2 minus, so you can fall on the fourth quadrant, or the fourth aspect of the part of our graph we've not used. And that will give me plus 2 somewhat here. We're already there. And minus 2 somewhat here. So we'll connect the two of them together. So this is it. And then this is my z5. Z5. So that's all about the Argand diagram. You can try the following on your own. So you can try this now. Next we'll look at is the polar form of a complex number. Before going straight into the polar form of a complex number, I would like to say certain things about trigonometry. You know, in our trigonometry we have the quadrants. So we have the first quadrant. We have the second. We have the third. And then we have the fourth quadrant. Now, one important thing is that the first quadrant is for angles ranging from 0 degree to 90 degree. And then we have the second quadrant. This is for angle ranging from 91 to 180 degree. We have the third quadrant, which is for angle ranging from 181 to 270 degree. And lastly, we have the fourth. It is for angles for 271 to 360. So that's how we get this about this quadrant. And now, you see, I like using theta 1, or it's important to use theta 1 for your first quadrant. So anytime you see theta 1, it means a first quadrant angle. We have theta 2 to be our second quadrant angle, theta 3 to be our fourth quadrant angle, and obviously theta 4 to be our fourth quadrant angle. Now, you see, there's an easy conversion from first quadrant to under quadrant. Theta 1 actually, I don't need to convert that. I'm looking at converting from second, third, fourth to first quadrant, or from first quadrant to those angles. You see, well, at theta 1, the relationship between theta 1 and theta 2 is theta 1 is equal to 180 minus theta 2. Another relationship between third quadrant and theta 1 is that theta 1 actually is equal to theta 3 minus 180. And then a relationship between first quadrant and fourth is that theta 1 is equal to theta 4. Sorry, 360 minus theta 4. Now, you see, I could give you 20 degrees now and ask you to convert it to first quadrant, to fourth, third, or second quadrant, sorry. Now, first of all, I need to realize that this 20 degree is a theta 1 value, meaning it's a first quadrant angle, because you can see 20 degree. Now, if I'm to convert to theta 2, I just simply need to write my relationship that theta 1 actually is equal to theta 2, 360, 180 minus theta 2. So because of this now, I can say that since theta 1 is 20 degree and I want to get theta 2, then we can say theta 2, if you make theta 2 so your formula, that will give us 180 minus 20, that's 160. So the equivalent of 20 degree on the first quadrant is 160 on the second quadrant. I would have said convert that 20 degree to third quadrant. Again, just write your relationship that theta 1 is equal to theta 3 minus 180. And then theta 1 given to you is 20 degree. And you're looking for theta 3. So you can just make theta 3 so your formula. Theta 3 will just simply be 20 plus 180, and that is 220 degree. So you can even convert to fourth quadrant. Let me convert the 20 degree to fourth quadrant now. What would that give to me? Well, this is that theta 1 is equal to, so this is 200, not 220. Pardon, please. Theta 1 is equal to 360 minus theta 4. And then, obviously, theta 1 given to you is 20 degree. You want to convert to fourth quadrant. Make theta 4 so your formula. So theta 4 will simply be 360 minus 20 degree. And that will give us 340 degree. We will need this knowledge as we take the complex number. But before we go into that, let's define some things about polar form of a complex number. The polar form of a complex number is a representation of complex number using trigonometric ratios. Another thing we need to talk about is the moduli of a complex number. You see, moduli or magnitude of a complex number, if a complex number is given as z equal to a plus b, we then know that its moduli can be written like this or can be written as r. It's represented by r. Moduli of a complex is represented by r. I can write as moduli of z or magnitude of a complex number, the same. This is simply a square plus b square all into square root. Another thing I want to talk about is the angle of a complex number, which is known as argument of a complex number. The argument of a complex number is the angle the complex number makes with the positive x-axis actually. And that arc of z, or you say theta, is actually given as tan inverse of the imaginary part over the real part. You can also say theta is equal to the tan inverse of imaginary part over the real part. Let's take an example now. Example 1. This question says represent z equal to 3 plus 4i in polar form. First of all is to get your r, which we call the magnitude of z or moduli of z, which is 3 square plus 4 square all into square root. This will give us 5. The next thing is to get our angle. The angle, which is arc of z, same thing. is simply tan inverse of 4/3, imaginary part 4/3 part, and that gives us 53.13 degree. The next thing to do is to ask yourself, what quadrant does this complex number fall on? Is it actually the first quadrant? How do I know that? Just simply try to draw it on the Argand diagram and see where it falls into. Since we have +3 on the real part, on the x-axis now, imaginary part is 4. So you see that when you draw this complex number now, it will fall on the first quadrant. So simply is on the first quadrant. So the angle you will use is the first quadrant angle, and since 53.13 is the first quadrant angle, you have to use it. So your complex number z can simply be written as 5 into bracket cos 53.13 plus I sine 53.13. That's all. Now, you see, if you multiply 5 by cos 53.13, you get 3. Multiply by 5 by I sine 53.13, you get 4i. And that actually gives you a complex number. Let's take example 2 now. So for this example 2, the question says represent in polar form -2 plus 3i. That is the first question. I look for the moduli. Square the real part, square the imaginary part, all into square root. Now to get my argument of z, it is tan inverse of 3/2. And that gives us, in getting my angle, you see, I didn't use -2. Actually, it's not a mistake, or maybe I forgot. Forget about using the angle. Forget about if you have a negative real part or a negative imaginary part. Use it as just the absolute value, which is 3/2. Now, but since this complex number is on the second quadrant, how do I know that? Try to draw and see. The real part is -2. So, -2. And the imaginary part is 3. So when we draw, it will fall on the first quadrant. So it will fall on the second quadrant. Thank you. So I have to use the second quadrant angle. So my theta will be equal to, you know, I have to convert to second quadrant. Theta 1 is equal to 180 minus theta 2. And your theta 1 we got when we for the arg is 56.31. So 56.31 now is equal to 180 minus theta 2. So my theta 2 will be 180 minus 56.31. And that will give me 13 cos 123.69 plus I sine 123.69. And you can see that if you multiply root 13 by cos 123.69, you will have -2. And when you multiply root 13 by I sine 123.69, you also have +3. But if you have used 56.31, when you multiply root 13 by cos 56.31, you would have 2, not -2. That's why it is important to convert to the second quadrant before representing the complex number. Let's take another one now, the second question. As you look at this second question, you see magnitude is, the real part is -1, the imaginary part is -1. So square all into square root, I get the r, which is the moduli of z, the z2, and that is root 2. Now the angle, I will forget about the minus. I'll use the absolute value, that is their number without the negative value. So that will be 1/1, and I will have 45 degrees. The next is to ask yourself, what quadrant does this complex number fall into? Well, obviously, since we have minus, it will fall in the second quadrant because the real part is -1, the imaginary part is -1. By the time you join, you see that it falls on the third quadrant. So we have to convert 45 degrees to third quadrant. How do we do that? This 45 given to us is a theta 1. So we just simply say that theta 1 is equal to theta 3 minus 180. This is the relationship we say we have then. So simply 45 is equal to theta 3 minus 180. And then we can say theta 3 is simply 180 plus 45, and that is 225. 225. So we can now represent our complex number. So it will be that our Z2 is simply equal to, the magnitude is root 2, then multiply by cos 225 plus I sine 225. So that's just that about that. We can take the number 3 now. Well, for this third question, our arc, which is magnitude of z or moduli of z, is equal to 29, and then arc of z is 21.8 degree. You see, I did that without putting the minus 2. Take the 2 and the 5. Now the next thing is to ask yourself, what quadrant does this fall onto? Well, this is the fourth quadrant, and it's simple. Just looking at this, you will know. Well, the real part is minus 2. The real part is plus 5, plus 5. And the imaginary part is minus 2. So you see, when we join these two and draw our complex number, it will be like this. And this is the fourth quadrant of our angle. So simple. Convert to first quadrant. We've gotten the theta 1. Convert to first quadrant. Where theta 1 is equal to 360 minus theta 4. So simply, theta 1 will be, this will give us that theta 1, which is 21.8. You want to convert to theta 4. So is equal to 360 minus theta 4. So what will theta 4 be? Theta 4 will simply be 360 minus 21.8. And you see that will give us 338.2. So we can now say that Z3 actually should be root 29 into cos 338.2 degree plus I sine 338.2 degree. So that's all. And you can confirm your complex number by just multiplying the root 29 by your cos or sine. You said you have actual value. But if you've used that in 1.8, you won't have that answer. So let's take the last one. Last one is quite an easy one because it's a first quadrant complex number. You can try that on your own as well. And if you do that, you actually have what I got here. So that's that about that. And you don't need to convert here. The reason is because this is a first quadrant complex number. So you can try the following exercises on your own. So try this, and the answers are given below.